That's a graphical explanation. It makes a lot of sense to me. I love to think of things visually, but if you are the kind of person who likes to think about things more mathematically, or if you'll feel more confident and believe it more if we explain it mathematically, you can get the same result by taking a look at the math and doing a couple of simple approximations. So let's look at that. By using the fact that r is much greater than r prime, and starting with this expression for magnitude r minus r prime, we can get to exactly the same place. The first thing we have to do is factor out r, in which case we get, and this is an exact equality, r times square root of 1 plus r prime over r squared minus 2 r prime over r cosine psi. So far, so good. 2, we make our first approximation. Throw out r prime over r squared, because we have said that r is much greater than r prime. We want to care about variations, about small scale variations, because we have this phase term to deal with, but this term is very small and is going to be dominated by the r prime over r term that's not squared. So then, this is an approximation, we end up with r times square root of 1 minus 2 r prime over r cosine psi. Step 3, we look at the Taylor expansion of square root of 1 plus x, which equals 1 plus x over 2 plus some other terms in higher orders of x. In this case, x is actually minus 2 r prime over r cosine psi, meaning that what we actually have now, this is our second approximation, is r times 1 minus r prime over r cosine psi. Or, if we simplify that a little bit more, r minus r prime cosine psi. Same answer as before that goes into the phase term. A key thing to note is that you can also write this as r minus the vector r prime dot r hat, the unit vector along the direction of r. And that's because for any two vectors, a dot b is equal to the product of their magnitudes times the cosine of the angle between them. So having done this, we've really simplified the radiation integral, and it makes it actually possible to evaluate for some small antennas. Here's what it looks like now. The magnetic vector potential at some observation point r is mu over 4 pi times e to the minus j k r over r. Hey, that's the same phase term that you see in a lot of spherical spreading out things. I told you before that in general for antennas the electric field has this e to the minus jkr over r dependence because everything is spherically spreading out from finite sources, and there it is, that's where it comes from. Then we have this term, this integral that accounts for the phase variation over the body of the source. So, integral over the sources of j, and I'm going to write these in Cartesian coordinates because we can learn something from the Cartesian expression here. X prime, y prime, z prime times e to the j, k, times e to the j k sub x, x prime, plus k sub y, y prime, plus k sub z, z prime. That's our new radiation integral. This is nice. Exponents are really simple to integrate, and we have a simple dependence on the distance from the source. But it's not only that. This part is a 3D Fourier transform. I know you're used to thinking about Fourier transforms in terms of time and frequency, but this one moves between 3D source coordinates and what we call spatial frequencies, or angle space. Let's go into that a little bit more. Where do I get these kx, ky, and kz terms? What do they mean? Well, it all comes from this expression, k times, remember that one of the expressions that we had here was r minus r prime dot r hat. Well, if I do k r hat, k r hat is a vector k that has different components. And the components of k are kx, where that is equal to k times r hat dot x hat, ky, which is k times r hat dot y hat, and kz, which is k times r hat dot z hat. And these work out in terms of the spherical coordinates angles. So that works out to be k sine theta cosine phi. Ky works out to be k sine theta sine phi. And kz turns out to be k cosine theta. And kz works out to be k cosine theta. These are the projections of r hat onto Cartesian unit vectors. We also refer to the sines and cosine part, but not the k, as direction cosines. For that reason. The fact that the radiation integral is a Fourier transform has a lot of really interesting consequences. And we're not going to talk about them right now, but we are going to talk about them in the next couple of weeks of class, or at least in our next couple of videos.